fermionic quantum processors with neutral atoms. And just again, quick announcement after this talk, we're going to be taking a group photo out on the terrace outside. No, you should have this. That's right here.
Can you hear me?
Yes.
Yeah? Okay. Wait, sorry. This one?
Yes.
Forward, backward. Great. Okay. Yeah, thank you. So I'm Robert. I'm a postdoc in Innsbruck. And we've had these very beautiful talks by Misha Dukin and others who explained to us how we can realize quantum processes based on cold neutral atoms. So today, what I want to talk to you about is this question of, do we have an opportunity and what kind of challenges are associated to creating a quantum processor that's fermionic inherently with fermionic neutral atoms? So I want to use this opportunity to thank my collaborators, both at home in Innsbruck and abroad. And also I want to highlight a recent work of Alexander Schuckert and his colleagues from UMD. I think Alex is in the audience here. So please, if you're interested in these questions, please also find him, talk to him about it. OK, why fermions? So as you know, there are a lot of fermionic systems in nature. So, and we've heard of these days about these very interesting examples. There's high energy physics. Fundamental particles are made of or are inherently fermionic. In quantum chemistry, of course, we have fermionic electrons. And also in condensed matter systems, there are strongly correlated electron systems. And all of these systems, what they have in common is that they have a very interesting fundamental spin statistics in these particles. So essentially what that means is, and here I already show a sketch of a tweezer array, this direction is going to go. But basically what happens if you have two fermionic particles and you interchange them, then the many-body wave function gets this minus sign. And that's a very fundamental thing. So if you think about quantum simulation, and here I just used chemistry as an example, there are essentially two routes you can go to realize that fermionic exchange statistics. So there's the one side that I call algorithmic encoding. So basically, you use something like qubits or some sort of bosonic quantum hardware. And what that means is you have to take care of this fermionic exchange statistics essentially through the algorithm that you run on your device. And there's a lot of interesting work that has been doing with this. There are very efficient ways of doing that. And also there are some really nice experiments, and this is by no means a complete list. One of the experiments was yesterday by Simon Everett's talk. And essentially, what these experiments have been done is they have used bosonic hardware, but nevertheless simulated fermionic dynamics. So I want to highlight in this context the neutral atoms here, because the neutral atoms have this very nice property that they can be trapped and cooled and manipulated in this very high controlled way. But also they come in two types. They come as bosonic atoms and they come as fermionic atoms. So that's sort of the second column that I want to highlight here. And this is an effort that has been going on in the direction of analog quantum simulation for quite some time. And there are more examples that I can list here. But basically, the idea is that, OK, if we have fermionic atoms, why not make use of them to directly sort of in the hardware component of your processor get this fermionic exchange statistics? So the idea that we sort of envision here is to combine these concepts. So the question is, how do we combine a fermionic processor based or like a system of cold fermionic atoms, as shown here on the left, together with these new technologies coming up and the promise of getting high connectivity and high control with optical tweezer arrays. So the idea is to combine this to a fermionic quantum processor, which has hardwired fermionic statistics for free, in a sense. OK. So, well, to remember you again, sort of the kind of idea that we have is, OK, suppose you have n fermionic modes that you want to simulate in your model, and you have n fermionic modes represented by these tweezers here, and each of these tweezers can either be occupied, so it's kind of 1, and if it's empty, it's kind of a 0. And then you have this high controllability and connectivity, so you can start to exchange the particles. And whenever you exchange two fermions that are, or two tweezers that are actually occupied, then you get this additional minus sign. OK, so my collaborators in Innsbruck and also collaborators abroad, they have come up with a blueprint of how to realize such a fermionic processor. As I said, you have this array of tweezers. They can be unoccupied, they can be occupied. And essentially, you can realize a fermionic Fock space in this way. But once you have that, what you need is gates. Yeah? You need digital controlled operations to actually run this processor. And they've suggested two kinds. For instance, there's this one gate over here. So essentially, this realizes a tunneling gate. Right? So what you can do is you can take the tweezer, and as I've shown, you can bring them together. You can realize a physical tunneling operation for a certain time with a certain angle, and you can separate it again. And you can essentially realize this unitary operation here with arbitrary angle. There are different ways of doing it. And on the other hand, there is this sort of well-established, known way of using Rydberg interactions here to get density interactions between modes. Yeah, so basically, you can imprint a phase depending on whether or not these fermions are occupied or not. So once you have these as building blocks, what you can do is you can put them together and form more complicated gates. For instance, the top one is a gate that implements a tunneling between mode I and K, depending on whether J is occupied or not. But the upshot of this slide is that with this, you can realize a universal processor that allows you to decompose any unitary that you want to realize. And there's one detail, because since the atom number in this system is conserved, therefore also the kind of operations that you realize should be particle number conserving. And very often in this side of setups, like in chemistry and so on, it's not a problem because also in the molecule, the number of fermions is conserved, right? So you should be fine. And so that works. However, there's one question. So since we have these gates, and of course these gates will be noisy, how do we implement quantum error correction on top? And it turns out that implementing quantum error correction, at least in a naive way, clashes with this constraint of having a finite sort of total particle number in this system. Right? So if you think about how usually one thinks about quantum error correction, you decompose your state into like tensor spaces and so on, and then you apply your strategies here. But already that thing is sort of broken here, because here we're talking about Fock spaces rather than tensor spaces. Right? So it's very hard to sort of individually address individual mode of the system without taking these global conservation laws into account. So I want to walk you on the next slide a little bit through this challenge and also recap some basics about quantum error correction along the way. So quantum error correction. Quantum error correction means we want to protect quantum states by encoding it into a suitable subspace of many particles, or few. So essentially what that means here, I'm showing an example of a repetition code. If you sort of use this redundancy to encode the information not in one, but in this case into three modes, and here I'm talking about spins, what happens is if you have something like a dephasing operation, you see it doesn't directly couple to the quantum amplitudes alpha and beta, but instead it just changes the structure of what you call the code words. So then what you can do is you can do these syndrome measurements. In this case, look at these operators x1, x2, and x2 and x3. And basically from the parity of these operators, you can infer whether or not an error has happened. And indeed here, if you measure x2 times x3, you would see that the measurement outcome is -1, and it would indicate an error. So the reason why it can indicate an error is because this stabilizer operator, it anti-commutes with the operator that represents your error to begin with. Okay, so it's this anti-commutation relation that's sort of the underlying reason why this works. So let's look at it for fermions. So suppose I have this array of fermions. I have them in the tweezer. Some of the tweezers, for technical reasons, might fluctuate, and you get a relative phase imprinted that you don't know and that you didn't want. So this essentially maps to this parity operator that I wrote here, 1 minus 2 times the occupation of this third mode. And the corresponding stabilizer operator, if you sort of generalize naively the quantum error correction strategies, would be this product of these C plus C dagger operators over here. So indeed, they anti-commute, so that should work. However, as you see, this is not a number-conserving operator, the stabilizer. So in practice, I will have a hard time actually measuring this. OK, so well, to summarize, usually if you want to protect against Z errors, you encode everything in sort of plus eigenstates. But actually realizing these plus eigenstates sort of in this occupation language here is very difficult. And the upshot is, if you want to realize a logical fermionic Fock state for these fermions, it cannot be implemented in number eigenstates of your system. OK, so well, one construction that we came up with is what I'm going to explain to you here on this slide. And essentially what we suggest is to use an ambient system, right? So if you bring in an ambient system with like sort of ancilla atoms, if you wish, and you carefully design the interactions between the system and sort of this, what we call a reference, then actually, if you look only at the system, you can make it look like you actually have different atom numbers superpositions within the system. So one way you can do that, and here I'm sort of sketching these kind of states, is suppose you have this reference system fully occupied and your tweezer system empty. So you want to create a mode. I don't just create it, but actually I take it from the reference system and bring it into the tweezer. And so mathematically what happens is we want to realize these effective fermion operators C, as opposed to the physical fermion operators S over here. So there's this conservation law for the S, but we want to have the operator C, which do not have this conservation law. And we do this by sort of supplementing this with this many-body operator R here. Okay, and then if this many-body operator R is unitary, and I'm going to show you an example next, then you can actually show that these anti-commutation relations of the S get translated to the anti-commutation relations of the C, and indeed the C's are again fermions then. Okay, so here's an example. Okay, yeah, so we have to show that they're fermions. So here's an example. Suppose I want to create two of these effective fermions, C2 and C3. So there's essentially two ways of doing that. I can first sort of put it into 3 and then into mode 2, or I can do it the other way around. So here what I'm doing is I first put this operator, I take it out of the reference, I put it into the mode 2, and then I take out another fermion of the reference, and I put it into mode 3. The other way around, if I do it the other round, you can see I can first take out a fermion and put it into mode 3, but then actually if I take out another one and put it into mode 2, I have to sort of cross the first one. Yeah? So I get an inherent minus sign from the underlying exchange statistics of the atom. So indeed, for this example, you see that these two operators anti-commute. And the reason why they do it is because I designed this many operator in exactly such a way that they do, meaning it's designed to always check all these reference mode and take out the last of these atoms and put it into the tweezer mode. And you can convince yourself that then this is a unitary operation. OK, so with that, you can create these number superposition states, as shown over here. And indeed, you see sort of the reference state is only determined by the number of atoms left. Yeah? Otherwise, it doesn't have any more structure. And that's sort of the underlying reason why this works. And if I continue, exactly, I wanted to make a reference to also Alex's paper again. So there are different ways of realizing such an operator R. And they choose a different route. So again, talk to Alex if you want to know. It's also very interesting. And so now if you go on with this, you can essentially, again, realize these code states with different atom numbers. you can make sure that you can define all the stabilizer and logical operators in a very analog fashion to CSS codes. And with this, you can realize quantum error correction. So if you have these three modes, they dephase, you bring in the reference, sort of let them interact in this controlled way, and you detect your syndrome, and you can correct for it. In a circuit language, it looks like this. So here, what we suggest is you can use extra ancilla qubits to read out the syndromes. And in fact, for each of these syndrome measurements, you have to interact with this reference. So again, you have stabilizer outcomes. You do the error correction by implementing a corresponding phase. So one thing that's left to be discussed is sort of how to realize this construction of this many-body operator R. And in fact, there's a decomposition that you can write down. And this decomposition, you can essentially plot like this. So indeed, it turns out that actually, if you want to do one round of error correction, it will be extensive in system size, sort of the number of gates that you have to run, because of this inherent many-body nature of this operator R. So one decomposition, what it does is you have the sequence of gates. So it runs through this reference system, and it's sort of looking for the domain wall. So it's looking for where's the last occupied mode. And once it detects the occupied mode, this blue circle means you sort of tunnel it into your tweezer. So, OK. Good. So with this, let me summarize. So I hope I convince you that it is possible to realize a Fermionic quantum processor and that you can implement quantum error correction in such a processor. I think there's a big question to sort of in what sense this will be useful. So can this be scaled up to a fault-tolerant system? And how would this be best done? So I've shown you one of these reference construction, but actually none of what I've showed you is unique. There are very different ways you could realize this. And what are best applications for that? So I've said there are very efficient ways of doing this algorithmic encoding, but I think it's a big question to ask, OK, where do these algorithmic encodings have trouble? Where do they lead to very sizable overhead? And can we sort of mitigate that by using such a hardware? And I think there's still big room to sort of explore quantum information applications in this realm of fermions. OK, so with this, let me thank my collaborators again. And I'm happy to take questions.
Thank you.